Good morning, everyone. Today we want to do a presentation for our analog electronic device assignment, which is topic about audio amplifier. Mm, Here is our group member list. So my name is Kwatekwa. I'm from 2 S1 So in this assignment, my job scope is to abstract and conclusion and also two presentation slide. So our group got three members, including me. So the first member is Kwatekwa, also from 2 S1. His job scope is to introduction and discussion, and he also do presentation slide. The second member is Chin Fulin. He also from 2 S1. He is doing calculation and result and also presentation slide. So for abstract, the purpose of this assignment is we can improve our understanding about the BJT transistor and the principle of the audio amplifier. So for this assignment, they have two transistors that we can use, which is BJT and FET. So we taking BJT as transistor in our circuit. Besides that, we also using multi-stage amplifier compared to single stage amplifier because this amplifier, multi-stage amplifier can result a higher output voltage compared to the single stage amplifier. Besides that, we also can take advantage to use multi-sim to complete the circuit design, which we can simulate the circuit that design online without using the component. So we can save a lot of time. Good morning, everyone. My name is Guatepo from 2BRZ S1 Today I need to present about audio amplifier. The audio amplifier is known as a power amplifier. It can boost weak electronic audio signals such as those from a radio receiver or an electric guitar increased to a power level sufficient for driving loudspeakers or headphones. They serve as the final stage in an audio playback chance just before the signal is sent to the speakers. The audio amplifier was invented around 1912 by Lee D. Forrest. Amplifier is then relied on transistor in 1970. There are four types of class of in amplifier: class A, class B, class C, and class AB. What is class A amplifier? The main feature of class A amplifier is the operating point Q of the amplifier is set near the midpoint of the load line, and the transistor is turned on during the entire cycle of the input signal. The class A amplifier can work in a single tube or push-pull. This single output transistor is biased around the Q point within the middle of its load line, and so it is never driven into its cutoff or saturation region. It can conduct current over the full 360-degree of the input cycle. Transient distortion and alternating distortion are small since the amplifier works in the linear range of the characteristic curve. The circuit is simple and the debugging is convenient. The efficiency is low, so the transistor power consumption is large. The theoretical maximum efficiency is only 25%. The second class is Class B amplifier. The Class B amplifier use a push-pull amplifier topology. The output of the Class B amplifier incorporate a positive and negative transistor. The Class B amplifier is twice as efficient as Class A amplifier with a maximum theoretical efficiency of about 70%. This is because the amplifying device only conduct for half of the input signal. This is why we can only conduct 180 degree. This allows the amplifier to idle with zero current, thereby increasing efficiency. Based on Class B amplifier, it has two transistors in a circuit, which is NPN and one is PNP. So, Class C amplifier. The Class C amplifier is the most efficient amplifier class, but the distortion is very high as it only has a small portion of the input signal is amplified. Therefore, the output signal bear very little resemblance to the input signal. Class A amplifier has the worst signal reproduction. The Class C amplifier is heavily biased so that the output current is zero for more than one half of the input sinusoidal signal cycle with the resistor idling at its cutoff point. So in other words, the conduction angle for the transistor is significantly less than 180, or you can say it's around 90-degree area. The last class A, which is class AB amplifier, this amplifier is a compromise between the class A and class B configuration above. While class AB operation still use two complementary transistors in its output stage, which is NBN and PNP, so it has a very small biasing voltage is applied to the base of each transistor to bias them close to their cutoff region when no input signal is present. The AB classification of amplifier is currently one of the most common used type for audio power amplifier design. This is because it can conduct angle between 180 to 360 degrees. So, as conclude, Class AB speaker amplifier offer a high signal to
Hi, I'm
noise,
Chifulin.
low total
The
harmonic
data
distortion plus noise,
that we
and
done and what we
typically
did
up
in this
to
project. Firstly,
65%
we set out
efficiency.
the design purpose of the circuit and the configuration and material chosen for this circuit. The software we're using to simulation this circuit is multi-sim, and report we write on the website, website with compiler XE latex. For the voltage gain of whole amplifier, because we are using single end amplifier, the output power VPP out is equal to VPP out square divided by 8 load impedance. So the load impedance is 8 ohm given from the data sheet, and 5 volt is the requirement. We can get it the 17.8 VPP or 6.3245 VRMS. So this is the minimum VPP required for the whole amplifier. This is the circuit we designed. Firstly, we using voltage divider bias with Darling-Done pair for amplify the voltage. After first stage, the VPP is not enough from the 17.8 VPP. So we amplify again by using same configuration. We get 18.9 VPP, and we using emitter follower to maintain the same voltage for the speaker, the load, to amplify the current. So to set up a voltage divider bias VDB, the voltage source should be enough to amplify the wave into destination magnitude by using formula VPP out. It's smaller than 0.9 VCC or VCC minus VE. Here is something paragraph. So we can choose the amplifier transistor through VCO and VBO that bigger than VCC. The IC continuous collector current also should be aware. Database will given a recommended collector current. The collector current is related to RC, or we can say output impedance, in a small amount potential difference for RC. Small collector current will be given a high RC, while bigger current will gain a low magnitude RC. Thus, collector current magnitude is chosen by reference what magnitude RC is needed. By starting design the VDB, the VE must be bigger than 0.1 of VCC, and the VC can be gained after VE gained the VCC plus VE divided by 2. The VC is set at the midpoint between VCC and VE to prevent clip of signal after amplified. And through the IC, and IC is similar to IE, we can gain RC and RE by using Ohm's law. For the base VB is equal to VBE plus VE, so we can also get the base current, and the I1 at here we can also call I prime, is bigger than IB 10 times, to prevent that, to ignore that IB taken away from I prime. So the R2 and R1 can be calculated using Ohm's law also. So for the voltage gain of VDB, actually is AV equal to negative RC over RE. But we want to enlarge the AV, we can put a parallel bypass capacitor with the resistor, can be included. So the AC emitter resistor becomes smaller, but does not affect the DC bias. The AV can be calculated through this formula. So, sorry. For the collector feedback bias, before setup, we need to know the load impedance, load current, and the VPP output we need. Through the VPP output, we can know the VCC, the main VCC we need, by adding VPP output plus VCE saturated from the datasheet. Through IL and IE can be decided. The IE must be bigger than IL, and IB can be gained through IE decided. Current through R1 and R2, I prime, is 10 times bigger than IB, and the ratio of R1 and R2 is 1 to 1. So we can simply get the voltage, basement voltage, voltage at base. So in multi-stage, the magnitude of R1 and R2 can refer to RC of the previous stage. That is 20 times bigger than RC at previous stage. So this is the correct circuit. So firstly, the input is 10 milliwatt, is the mic level voltage signal. Input to the first stage, and we gain 5.13 volt VPP, and this signal input again with AC coupling, and we gain 20.1 volt VPP, and we input this signal into the emitter emitter follower to gain the output. This is the oscilloscope from multisim. The channel A is 20 milliwatt per division, and channel B is 2 watt per division. Channel C and D is 5 watt per division. So for the channel A, the voltage line is green, and red for the output voltage of first stage, output voltage of second stage, and the final output is the green color, brown green color.
This project, we can discuss that the audio amplifier cannot be designed in single stage. This is because single stage configuration have a high load impedance, causes low current flow into the speaker. To overcome the least current flow into the speaker, the circuit is designed using Darlington transistor, which can help increase the current by doubling the amount of current flowing in one direction. Besides that, we also can lower the load resistor RC so that the current flow will be increased. The circuit can be designed using Class AB amplifier rather than using Class A amplifier. This is because the efficiency for Class AB is higher than Class A. Besides, in changing the classes of the amplifier, we also can increase the stage amplifier to increase the voltage gain. The more the voltage gain, the higher the power output. In conclusion, we can know that the transistor can improve the sound quality by amplifying the low signal input to a high signal output. Besides that, we also can know that the voltage gain is computed by output voltage and input voltage. As we all know, the voltage gain is equal to output voltage divided by the input voltage. So the last one is the multi-stage amplifier is better than single-stage amplifier in producing high output voltage. This is because the multi-stage amplifier is the combination of both stage voltage gain, while the single-stage amplifier is only for the voltage gain for single stage. So the multi-stage can produce higher output voltage.